Hi students, welcome to the session on pumping lemma for regular languages. And coming to our session objectives, understand the basic concepts of regular languages, study and analyze pumping lemma for regular languages, understand the closure properties of regular languages. These are the basic objectives for our current session. Coming to regular languages. Regular languages are languages that can be generated from one element languages by applying certain standard operations a finite number of times. That is standard operations. These symbol operations include the concatenation, union, clean closure, etc. Okay. They are the languages that can be recognized by finite automata. So, regular languages are languages that we can generate from a singleton language, that is a language with a single element, and when we continuously apply some basic operations on these sets, we will get regular languages. And we can say in another way, we can define in another way that a regular language will be accepted by a finite automata. Now the regular languages can be represented in four different ways. One is using deterministic finite automata. Another way is to by defining non-deterministic finite automata. Then the regular languages can also be represented with the regular expressions and also with the regular grammars. Okay, so these are the four different ways to represent a regular language. In other words, we can say any machine or any DFA and NFA, if a language is accepted by NFA or DFA, those are regular languages. Or if we can represent any language with regular expression, it is also a regular language. And if we can represent any language with regular grammar, that is also a regular language. And coming to the closure properties of regular languages, the regular languages are closed under union, concatenation, star, reversal, complement and intersection. Okay, so these are the basic operations that we can apply on any regular languages. Okay, so coming to union. Union, if suppose L1 and L2 are two languages, two regular languages. Okay, and when we take the union of these two, we will get another regular language. That is why we say regular language is closed under the operation union. Okay, so this will also be regular language, union of L1 and L2. So remember, L1 is a regular language and L2 is also a regular language. Then if we take the union, it will be another regular language. And similarly concatenation. If L1 and L2 are two regular languages, and if we take the concatenation of those two languages, we will get another regular language. So this is also a regular language. Then star closure. Okay, so if L1 is a regular language and if we take the star closure or clean closure of this language, this one L1 star will be another regular language. Then reversal. If L1 is a regular language and if we take the reverse of L1, that is if we reverse every word, every string in the language, this one L1 reverse will also be another regular language. Then complement. If L1 is a regular language, then L1 complement will be a regular language. And intersection, if L1 and L2 are two regular languages, and when we take the intersection of these two, it will give you another regular language. Okay, so that is why we say that regular languages are closed under these six operations, that is union, concatenation, star, reversal, complement and intersection. Okay. So in short, we can represent it like this. So is assume L1 and L2 are two regular languages. Then when we apply these operations on these languages, we will get another set of regular languages. L1 union L2 is a regular language. L1 concatenated with L2 is another regular language, L1 star is another regular language, L1 reverse is another regular language, L1 complement is a regular language, L1 intersection L2 is also a regular language. So these are the closure properties of regular languages. Now coming to the pumping lemma. So why we use pumping lemma means how we prove that a language is regular or not. Okay, so one thing is, if I can define a DFA or if I can define an NFA for the given language, I can surely say that it is a regular language. But if suppose in some cases for some languages it may be very difficult to find out a DFA, or we may be going in a wrong way and defining, we are ending up with not able to define a DFA, that case we cannot surely say that it is not a regular language. So for that we need a lemma. Okay, so for that purpose we use the pumping lemma to show that a particular language is regular or not. So how we start with the pumping lemma? So first we assume that we have a regular language L, okay, and if it is a regular language there will be a DFA corresponding to that language. Okay, so for every regular language we can define DFA. Then assume that it has m number of states. So if this is the DFA that represents the language L, then we assume that it has m number of states, including the initial and final state. So this number you have to remember, m, that is the number of states. Now we consider a string W that belongs to, we consider a language W that belongs to the language L. Okay, string W belongs to L. So if W is belong to the language L means, if we start from the initial state, we can go through, we take every character in W and it will take one transition, first character, second character, like that will take one transition, and last character we will move to the final state. So that is a walk. We can say that it is a walk from the initial state to the final state, and over the walk every transition is labeled with one character in the string W. Okay, so we introduced a m and we introduced the string W. Okay, now another constraint we are putting up here is, if this length of W is greater than or equal to m, means m is the number of states in the DFA, m is the number of states in the DFA, and if the W, if the string W has the number of characters equal to m or greater than m. Okay, so we can take one simple example. Okay, so we have one state Q0, Q1, Q2. Okay, so only three states I have. Q0 is the initial state, and this is A, B, and this is B, this is A, like that. Okay, assume that this is a DFA that accepts any string which has at least, which contains at least one B. Okay, that is the language. So in this case, if I take W, here the number of state is 3. So W is equal to, if I say A, B, B, okay, it should be accepted because it contains at least one B. So it should be accepted. So what is the length of W? Length of W is equal to 3. That means the number of states. So in this case you can see, if suppose if W is equal to A, B, the number of the length is less than 3, the number of states. So it will take this transition and this transition, and it will reach the final state. And if it contains one more character, it means that what will happen, one string, one state will be repeated. Here you can see that the Q2 will be repeated. Q0 to Q1 we move, and from Q2 again Q2. So here we can see that one of the state will be repeated. Okay, so if this condition is satisfied, then at least one of the state will be repeated over the walk. from the initial state to the final state. So we call it as a pigeonhole principle. Okay, so this same principle we are going to apply in this pumping lemma. Okay, so let Q be the first state that is repeated in the work. So assume this is the machine we have, and Q may be the state that can be repeated in any string, okay, when we consider. So in that case, what we have to do, we have to split the W as 3 different parts. The string has to be divided into 3 different parts, which is called X, Y, Z. And now X is called the part just before the repetition one, repeating state, and Y is the part where the repetition happens, okay, and Z is the part after the repetition. Then one more condition is there, the length of xy should be less than or equal to m, and the length of y should be greater than or equal to 1. That means the repeated part should be at least 1 character, or at least 1 character should be repeated there, okay, that is mandatory, and the length of xy should be less than or equal to m. Now if this in this case the string xz will be accepted, because from x we will reach q, and from q with z we will reach the final state. So xz will be accepted, and if y can be repeated once, x, y, z will be accepted in this case, and this y part can be repeated any number of times. Okay, so I can repeat y, I, z any number of time I can repeat. All those strings should be accepted by the machine, or it will be accepted by the machine. In other words, all these strings will belong to our language. So in general, the string x, y, I, z belongs to L, where I is equal to 0, 1, 2, 3, etc. Okay. So the statement of pumping lemma is like this: given an infinite regular language L, there exists an integer m for any string W belongs to L, with the length of W greater than or equal to m, and remember m is the number of states in the machine. We can write W is equal to xyz, where length of xy is less than or equal to m and length of y is greater than 1, such that xyiz belongs to L for all I from 0 to n. Okay, so that means that if xyz is in the language, then xyiz should also be in the language if it is a regular language, and when this won't happen, and when this condition won't agree or won't come, it won't be a regular language. Okay, so that is the point we have to remember. If the string xyz belongs to the language, then xyiz should also be in the language. When it contradicts, it will not be a regular language. So let us take an example, the application of pumping lemma to prove that a particular language is not regular. So we take a raised to n, b raised to n as the example language, where n is greater than or equal to 0. We have to prove that it is not a regular language. Okay, so for that we apply the contradiction method. So first we assume that L is a regular language, and we are going to apply our method. Let m be the integer in pumping lemma, and pick the string W such that W belongs to L and the length of W is greater than or equal to m, and let W is equal to a raised to m, b raised to m, and split it W as xyz. So this is xyz, a raised to m, b raised to m, that is m number of a's followed by m number of b's. So we are dividing this like this, first few a's are x and the next few a's are y, and the remaining as z. Likewise we are going to divide. And what happens if we repeat y any number of times, that string should also be in our language. So let us see what happens. Okay, so we take y as k number of a's are there, assume that, and we apply, or we are going to repeat the y part. Okay, so what will happen if I repeat y 2 times, that is if x, y, 2 z, y part will be repeated 2 times. So y part will be repeated means here one more k k number of A will be added along with this. So the total number of A will be m plus k, and total number of B will be m only, remaining as the same. So I can write this string as A raised to m plus k, B raised to em. Okay, B raised to em. And obviously this is not belonging to the language A raised to n, B raised to n. Why? Because we need equal number of A and equal number of B. Here you can see that the number of A and number of B are different, and obviously this is not belonging to the language. And in other words, we can say that this xyz, xy2z is not belonging to the language. So if it was a regular language, this should also be in the language, and since it is not in the language, we can say that the given language A raised to n, B raised to n is not a regular language. Okay, so that is all about the pumping lemma, and why we use pumping lemma is to prove that a particular language, a given language, is regular or not. Okay, and going through the questions, and thank you, students.